All right, guys, I want to make a video very quickly of our lesson for day 2 of Unit 9. So the first thing is go over long division. I know it's been a little while since you've done this, but just to have a quick review of it. So we have x squared minus 18, which is obviously the portion that goes on the inside. And then x minus 2 is our divisor. It's on the outside. Now, the one thing we have to be careful with this x squared minus 18, we put it on the inside. Remember, we have to account for all the terms. So we have x squared, and then we have a missing term right here with where our x term would typically be. So we're going to have to account for that position. So we'll say plus 0x minus 18. So now what we do is we just look at the first term, both of these pieces. So we'll look at the x and we'll look at the x squared. And we're just thinking about, well, what could we multiply x by in order to get x squared? All right, well, x times x is x squared. Okay, some people think of it division-wise, like x squared divided by x is x. That's fine as well. But once we figure out this term, I like to put it above the term that I was working with. So I like to put the x above the x squared. That's what we're doing first. And then we'll just take this x and distribute it back over here to the x and the 2. So x times x is x squared. And then x times negative 2 gives us that minus 2x. And then just like you've always done in the past with long division, you always subtract. So you may have heard your teachers in the past just basically say, hey, just change the signs on everything. So we'll change that x squared to a negative. And this 2x is now a plus. These first two should always cancel out. They should always combine to give you 0. So now we're left with 0x plus 2x, which is 2x. And then we'll bring down the next term we haven't used, so 8 or minus 18. All right, then we say, well, 2 times x would give us 2x, so that's a positive 2. We'll distribute that 2 back over here, so 2 times x is 2x. And 2 times negative 2 is negative 4. Remember, we'll go back and we'll change everything. Because since we're subtracting, we'll change the signs. This 2x is now a negative 2x. And that 4 now becomes a plus. So there's 2x and negative 2x is 0. So we're left with a remainder of negative 14. So if I were to ask for the remainder, you just tell me negative 14. But if we're talking about the full quotient, everything, accounted for, then this is how we handle the remainder. So that negative would make a minus sign up here. And then the divisor x minus 2 is always on the bottom. And then we write our remainder 14 on the top. So we'd have x plus 2 minus 14 over x minus 2. Okay, so there's a quick reminder there of long division. And so now we're going to talk about, here we go. Here's our notes. It's on Class Kick and on Canvas as well. It's the real zeros of polynomial function. And here at the beginning, it's a lot of division of polynomials, and it goes into terms associated with it, things you've had in the past. But just to kind of keep this video a little bit more streamlined, let me jump down here to what we call the remainder theorem. Okay, and if you have a polynomial function and you divide that function by x minus c, then the remainder is always f of c. All right, so right here in example 1, here's our polynomial. We're going to divide it by x minus 3, and then we're also going to divide it by x plus 2. Okay, so this is a good opportunity for me to do the other part of division that we typically run into, is we have long division, but we can also do synthetic division. So we're having x minus 3 right here. That's what we're dividing by. So if x minus 3 was the factor, right, if we were trying to figure out what makes this equal to 0, if you want to think of it that way, basically we're saying 3. So what we'll do is we'll always write 3. Remember, synthetic, and it's been a little while, you put a little box like that. And then what we do is we just go through our polynomial. So we have x cubed minus 4x squared minus 5. And we're just concerned with the coefficients and the constant. So for instance, x cubed has a coefficient of 1. So I'll put this 1 right over here. All right, our next term is negative 4x squared. So we're going to put negative 4. All right, then we have, well, we have a missing x term. So just like with long division, we need to account for that within our synthetic. So I'll put that 0. And then we have our constant negative 5. Okay, so now we're just going to go through this process once again, or for the first time rather, I apologize. So here's our synthetic division. Here's how we do that. We draw a little bar right down here. We always bring down the first term. So 1. And then it's just the same process over and over again. We're going to take our number right here in the box, which is 3, and we're going to multiply it by the numbers that are below this red line right here. So we're going to go 3 times 1. So 3 times 1 is 3. And then we're going to combine negative 4 and 3. Okay, so after you multiply that 3 times 1, you put that number right here under the next number that we haven't worked with, coefficient or constant if it's at the very end. But we're going to take negative 4 and 3 and we're going to add them. So that will leave us with negative 1. All right, and then we'll take 3 and multiply it by negative 1 now. So we're always going to do the same process. So 3 times negative 1 is negative 3. And we would write that negative 3 right here below the 0, the next number in our sequence here. So then we would combine 0 plus negative 3 is negative 3. And so the last time is 3 times negative 3, which is negative 9. Negative 5 plus negative 9 is negative 14. Okay, so that's how we do synthetic divisions. Very similar. Well, it accomplishes the same thing as long division. Okay, but it's just a different approach of doing division. All right, so what this question was wanting, remember, is what is the remainder if that portion is divided by x minus 3? So the remainder is always the last part of the synthetic division. So the last number that we were able to combine to get is negative 14. This part that I'm boxing right now. So negative 14 is our remainder for this problem for part A. Okay, so negative 14 is a remainder, and I'm gonna go back up to this theorem. If f of x is divided by x minus c, which is what we did with the synthetic division, then the remainder is just f of c. So remember, we did the synthetic division. This 3 right here, what this theorem is saying is that f of 3 is actually equal to negative 14. So when you do in this problem, if I asked what is the remainder, you could go and you could do synthetic division or long division, or you could just go plug in this case 3, and get what the remainder is. So like for part B, you can, instead of doing synthetic or long division, if I just want to know what is the remainder, all we have to do is just say, well, what is f of negative 2? We can figure out what f of negative 2 would be. I believe that's negative 29. Just if you're wanting to go and check that. So that means our remainder, if it was x plus 2, would be negative 29. Now, the next theorem is the factor theorem. And really, it kind of goes hand in hand with remainder. It's just a specific case. Basically, what it's saying is if you did synthetic division or long division, or if you were to go and plug in that number to the polynomial, if you get a remainder of 0, or if you get f of c as 0, then that's something that's important. So if f of c was 0, that means x minus c is a factor. Or if we go and we do long or synthetic division and we get that a remainder is 0, we find that f of c is a factor, well, that implies also that f of c is equal to 0. So it's just a specific case. So I'll do part A with you and kind of show you what it looks like. Use the factor theorem to determine whether that function has the factor x minus 1. All right, so what I had people in class do is I wanted them to do synthetic division because we wanted to practice it. But if you're just trying to figure out if that's a factor, you could just go, I'll just write over here to the side, you could just go and figure out, right, what is f of 1? And see if you get a remainder of 0, if you get equals 0. All right, but I'll do a synthetic again, just like I did in class, just so you guys can see it one more time. So that means we have 1 right there, because that's what would make this equal to 0. And we're going to divide that into 2x cubed, so 2. And then we have minus x squared, so negative 1. 2x, so 2. And then our constant negative 3. What we can do is we can just go through this whole process, right? So 2 goes right there, multiply, 1 times 2 is 2. Combine negative 1 and 2, you get 1. 1 times 1 is 1. Combine 2 and 1, you get 3. Then 1 times 3 is 3. Combine negative 3 and 3, and you get 0. And since this last number, remember, which represents the remainder in synthetic division, since it's a 0, that means that f of 1 would equal 0, right? It also means that x minus 1 is a factor. So if I basically says it yes or no, so yes, it is a factor. All right. And I think this other one, if you checked it out and did the x plus 2, you can just look at the key, obviously on Canvas. But if you figure this one, it then comes out to something that's not a 0 as a remainder. So this one should be no for part B. All right. But just kind of keep them streamlined a little bit. The next to last thing we talked about was the rational zeros theorem. Sometimes I call it rational root theorem. Remember, zeros and roots are the same thing. And you can go through all this, but let me just kind of show you how it works. What we're going to do is we're going to list, first of all of the possible, all the potential rational zeros. Okay, and here's how you do that. 6 is our constant. Okay, we represent that with like a P, and 2 is our leading coefficient. So that's like the Q. So if you're kind of looking up here at this theorem, that's where they're getting the P and the Q. Basically, it's just a way of writing a fraction. Okay, and so here's what the rational root theorem says. You take this P, this 6, and you list all of the different factors of 6, all the numbers that would divide nicely into 6. All right, so that would be like, we're going to go plus or minus on everything. This will be a bit redundant, but I think you'll see where it goes at the very end. So it could be positive or negative 1. That goes into 6. All right, I don't really care about the minus sign right here, by the way. I'm just really focusing on the 6 because it's plus or minus. All right, so 2 plus or minus 2. That would go into 6. 3 and 6. All those go into 6 nicely. All right, I'm going to write that over the number in the front, which is 2. So positive and negative 1 go into 2 nicely. So we're doing the exact same thing, right in the factors. Positive, negative 2. Those go into 2 nicely. And so basically what we're going to do here is we're going to find all the different divisions that we can here, right, with these numbers on the top as a numerator and these numbers on the bottom as our denominator. So we could take 1 and 1, you can divide it. And since it's plus or minus, we're always going to have a plus or minus on all of these. So positive and negative 1, that's possible. Okay, the next combination is we can take 1 on the top and 2 on the bottom. So that means we can have positive or negative 1/2. Okay, after we have that taken care of, we jump up here to the 2. So we have 2 and 1. So plus or minus 2. And then 2 and 2 is 1. We already have that one listed. So now we go to the next one. We have 3. So plus or minus 3. And then 3 over 2. So plus or minus 3/2. And then the last one is 6 over 1. So positive or negative 6. And then 6 over 2 is 3, which we already have accounted for right here. So we have essentially 12 possible rational roots, 12 potential rational zeros right here for this polynomial, because we have 6 numbers listed and it's a positive or negative version of each one. And so what we have to do is we would have to go in here and just try each one of them and see if we would get a nice division, if it would go into it nicely, right? Whether it be synthetic or long division into our polynomial and see if it works. And there's other strategies to kind of help with that, but we'll kind of lead you as far as whittling it down as you're working through these and help you kind of have a more streamlined focus on which ones to focus in on. But what I will do is I'll show you on example 4 kind of how it works. So 4, see, it's the same polynomial that we had above. These are all the possible numbers that could work as potential rational zeros. So it says find the real zeros, but really I want you to find the rational zeros of this polynomial and write f in factored form. So maybe a number we can pick here, and obviously I kind of have an idea already, is 1. If you picked 1, and decide to try to do it. So I'm going to use synthetic division. So we have 2, 11, -7, and -6. So just going through our synthetic division one more time. Bring our 2 down. 1 times 2 is 2. 11 and 2 is 13. 1 and 13 gives us a 13. -7 and 13 is 6. And then 1 and 6 gives us that 6. So we have a remainder of 0, meaning that 1 is a rational root. Okay, it produced 0 as a remainder. So that means write f in factored form. If we had 1 as a 0, remember that we could write that as just x minus 1 when it's as a, an expression right there, x minus 1. All right, so there's x minus 1 first. And here's what happens. Every time we do synthetic or long division and we find one that works, like we did right here because we have a remainder of 0, it's going to take the degree of our polynomial and drop it 1 degree. So we have right here, here's the degree of our polynomial because it's the largest, it's the term with the largest degree is 3. Okay, so that's a cubic. After our division, this right down here, this 2, 13, and 6, we don't have to worry about the 0 anymore because that's a 0. This is now a quadratic. It actually decreased. So here's what that quadratic looks like. It's 2x squared plus 13x plus 6. All pluses because all these numbers are positive on the bottom right here. So what we could potentially do is we could then apply the rational root theorem again, right? Put all the different factors of 6 on the numerator, 2 in the denominator, which would be the exact same result we had earlier. So it doesn't really take us anywhere, but sometimes it actually does help you decrease your choices. But with that said, as you're doing this rational root theorem, you're constantly looking for, when can I start factoring? Okay, so there's 2 situations that you guys run into quite often. If there were like 2 terms, maybe you could do it. But there's 4 terms, that would be a potential opportunity to factor by grouping. Or if there's 3 terms like this, and it's a quadratic, okay, but really I could just be more general. Anytime you get to a quadratic, you need to stop and see if you can factor it because that's something you've done a whole bunch of. All right, there's no more reason to do rational root theorem. So in this case where we have a quadratic and we just see if we can factor that like we always have, which we can. All right, so this comes out to be 2x plus 1 and x plus 6. So 2x squared minus, or plus, 13x plus 6 would factor as this 2x plus 1 times x plus 6. So now we've written f in factored form, and it says find those zeros. Well, we found 1 earlier, right, when we were doing synthetic division. And then we can look at these. Well, 2x plus 1, that means -1/2 would be a 0, and then -6 would also be a 0. And I probably should write, I don't know if I have any space right here. This entire one right here that we factored is actually f of x, right? So we should probably have an f of x right there. So f of x equals that x minus 1 right there. Sorry, I'm having to annotate a little bit differently than usual, but I think you guys get the point. F of x equals x minus 1 times 2x plus 1 times x plus 6. Okay. All right, so the last thing is we did what's called the intermediate value theorem. Okay, and the intermediate value theorem is an existence theorem that talks about a continuous function not being able to, on an interval, cannot skip values. Okay, so intermediate value theorem, there's 3 conditions, 3 criteria, if you will, that you need to prove. And once you have those 3 conditions met, then you can say there's at least one number c in some interval such that f of c equals k. So here's what that means. Let me give you a visual first because there's a lot being said right there. Say we had some type of graph. All right, so this graph, let's make a random one here. Okay, so it looks like this. Okay, and I'm going to go ahead and do a specific case here. Just make it closed. All right, so if we had, say this value was 10 for that y value, and then this one down here was -8. Say the x value associated with this point is 7, and this one's -5. All right, so going through the intermediate value theorem, the first thing is we have to figure out, is this function right here that I've drawn, is it continuous? Well, yes, we can, we could make this graph without ever having to pick our pencil up. So this is a continuous function. That would be, number one, check. All right, now number two is it says f of a cannot equal f of b. Well, f of a, so f of -5, if you will, is -8. And f of 7 is 10. Well, -8 and 10 are definitely not equal. So there we go. Now I have two checks. We've taken care of two of the criteria. Okay, and the last thing it says is this. K is any number between f of a and b. So let's say that the number we were concerned with was 2. Okay, you can definitely see that 2 is between -8 and 10. So there's check 3. 2 is definitely between -8 and 10. So if all those three conditions are met, which we have a case in this example that I gave you that works, then there's at least one number c in that interval that f of c equals k. There's some c, which is, here's where 2 would be on our graph, right? Right there at that spot. There's some c right here such that f of c is equal to 2. So that's what it's talking about. There's a number right here in between. So 2 is in between -8 and 10 on this closed interval, right? And we know that on the closed interval, these two parts are not equal. So and there's a number, obviously, like I said before, between -8 and 10. There has to be some c, some x value, such that f of x or f of c is equal to 2. So that's all we're going to do right here. I'm going to do the first one with you, which is the same thing we did in class. We're going to use the intermediate value theorem to show that f of x equals x cubed plus 2x minus 1. This polynomial has a 0 in the interval 0 to 1. All right, so remember we have three things we need to show. First thing is we have to show that it's a continuous function on the interval. Well, f of x, right, is just a polynomial. All right, and so since it's a polynomial, it has to be continuous. I mean, it's a polynomial, so it definitely is a continuous function. We don't have anything that we're dividing by or anything like that. So f of x is a polynomial, so it is a continuous. So it is continuous. I'll just say that. And just to kind of stick with the theorem, I guess, on the interval 0, 1. And that's being a bit redundant. I mean, it is a polynomial, so it's continuous. But I'll just go ahead and say that since we have our interval, that's there for us. All right, so the second thing is we have to show that f of a and f of b are not equal. Well, our interval is 0, 1. So a is 0 and b is 1. So we would say, well, f of 0, we need to find that first. So if you plug 0 into this function right here, we would get -1. All right. And if we were to plug 1 in, we would get 2. So f of 1 is equal to 2. All right. So f of 1 is f of 0, sorry, is -1, and f of 1 is equal to 2. Those are definitely not equal. Therefore, f of 0 is not equal to f of 1. To kind of make it nicer here, mark that as so not equal to. Sorry, guys, I'll move this around a little bit here. There we go. And got it. So f of 0 is -1, f of 1 is 2. Therefore, f of 0 and f of 1 are definitely not equal to one another. All right, so we've gotten two things taken care of, the continuity, and we've shown that f of 0 and f of 1 are not the same. So the last thing we need to do is there some k between f of 0 and f of 1? All right, is there a number between -1 and 2, the number we're concerned with? Okay, the number we're concerned with is it says show that this polynomial has a 0 in that interval. Remember, that means that it's where it crosses the x-axis. That's when y is equal to 0. So we're basically saying, is 0 located between -1 and 2? Well, yes, of course it is. So since -1, I'll get it right, there we go, -1 is less than 0, which is certainly less than 2. All right, 0 is definitely between -1 and 2. We've now had all three of those stipulations met. Continuity, f of 0 doesn't equal f of 1, and our k, our 0, is between -1 and 2. Therefore, there must be some type of c, some c such that f of that c is equal to 0, right? The number that we're concerned with. And that is our intermediate value theorem. We showed all three of those pieces. So what I'm going to do is, actually, I saved this last one for in class next time. We're going to just talk about that as a group and kind of get us going again on it. So that'll give you guys an opportunity to ask questions if you have any. And that's it. Okay, that's basically our lesson for Unit 9, Day 2. If you have any questions, let me know. Have a great day. Stay out of the trees.